This video is for lesson 17-2 about similarity transformations. Learning goals are to understand the meaning of similarity transformations and use these kind of transformations to decide whether figures are similar. Let's continue the scenario about the work that graphic artists do. Let's say that there are two possible layouts of an image. We have layout A here and then layout B. First question we're asked is, can a single dilation centered at the origin transform layout A into layout B? Explain. I'll pause the video for you to give your input here. Hopefully you answered no. The dilation is able to change the size and take layout A, increase its size to create a heart that's the same size as what's in layout B, but a dilation cannot cause the rotation that we see in layout B. Number two, can a single rigid motion transform layout A into layout B? When you answer this, remember that the rigid motions are translations, which are slides, rotations, and reflections, which are flips. Number three, let's describe in words a composition that would map layout A to layout B. A composition is a sequence of transformations. We decided we can't do this only with a dilation, and we decided we cannot do this only with a rigid motion. So let's make a combination of these things. One sequence of transformations that would map layout A to layout B is to first dilate with scale factor 1.5. That enlarges layout A to the size that we need. Then we can rotate 90 degrees around the origin. Number four asks us to describe this composition using the function notation. We've learned different symbols to do this. The first thing that we said we were going to do is dilate. The symbol for that is a capital D. And then as a subscript, we say that we're going to dilate around the origin, comma, and then we give the scale factor, in this case 1.5. So there's our symbols for the dilation. Then put this in parentheses, and then on the left side, let's indicate that we're rotating. The symbol for rotate was a capital R. As a subscript, again, we're going to put O for the origin, and then we write the number of degrees that we're rotating. We're going clockwise 90 degrees. Clockwise rotations are negative numbers. So I'm going to write negative 90 degrees right there. Here are the symbols for the composition of functions. It has a dilation first and then a rotation. Next, let's try several practice problems. Number 5, perform the following compositions of transformations on the pre-image triangle ABC. Draw the pre-image and image on the grids. So we're going to start by drawing that triangle on the grid here for question A. I'll pause the video to give you time to do that. So here's what you need. All we were doing is copying triangle ABC onto this fresh grid. A is at 2, 1, B is 2, 3, C is at 6, 3. Make sure you have this correct before we do the reflection or the dilation. Okay, in question A, the first transformation that we're doing is the reflection over the line y equals 1. I'm going to show that in green ink. Now before I show that, I'd like you to try it. Just remember that the line y equals 1 is a horizontal line crossing the y-axis at 1. I'm going to draw that with a dashed line, and I suggest that you show that on your grid with a dashed line as well. This is our reflection line. We want to take that red triangle, ABC, and reflect it over that line. It's going to end up down in this area of the paper. I'll pause the video for you to draw that reflection. Here's the reflection shown in green ink. Hopefully that corresponds to what you drew. Please fix it if you need to. Next, we're going to do the dilation. So looking up here, the capital D means dilation. Our center is the origin, and we want to use a scale factor of 2. We want to make the distances twice as long. Let's work this one together. Notice that this point here is at 2, 1. If the scale factor is 2, we're going to multiply that ordered pair by 2. So over here on the left side, 2, 1, when you times by 2 would create the ordered pair 4, 2. So let's find 4, 2. It's right there. This is where that point ends up. That was called A prime. Next, let's take this dot right here, the bottom corner of the green triangle, and apply the dilation to it. This dot is located at 2, -1. When we times by the scale factor of 2, that creates the ordered pair 4, -2. Let's locate that over 4 and down to -2. There's that dot, and that is B prime. Okay, we have one more dot to locate. The end of the green triangle right there at 6, -1. So let's take the ordered pair, 6, -1, multiply by the scale factor of 2 to see where that dot moves to. This is 12, -2. So over to 12 and then down to -2 is located right there, and that is C prime. I'm going to take the blue pen and connect those dots together, and there is our new triangle. Notice that its size has changed. It's an enlargement of the original red triangle using a scale factor of 2. We first reflected to get the green triangle, and then we did the dilation to create the blue triangle. I'll pause the video for you to finish your drawing. Next, let's do question B. Remember that the first thing we have to do is draw the original triangle ABC in the correct location. Here's triangle ABC. This is the same triangle that we did in the last drawing, except the scale on our axis lines is a little bit different, and that's why this triangle looks different than that last red triangle. I'll pause the video for you to correct your triangle if you need to. The first transformation we're going to do is the dilation around the origin with scale factor 1/4. We want to make the triangle 1/4 as large. To do that, we can multiply that scale factor to the coordinates of points A, B, and C. You can do that in the left margin. First of all, with point A. Point A was located at 2, 1. I want to multiply those numbers by the scale factor 1/4 to see what I get. 2 times 1/4 is a half, and 1 times 1/4 is a fourth. So let's find that spot. Over to a half, and then up a fourth is only this far up. If you pay attention to the y-axis, if that mark is 1, then this mark is a half, and going only halfway to the half is a fourth. So here is where point A ends up when we do the dilation. I'm going to pause the video for you to do the same thing with points B and point C. Over here on the left side, show the work where you're timesing by the scale factor. This small green triangle is the result of that dilation. It's so small because our scale factor was a small fraction, 1/4. Next, let's apply the other transformation, which is this portion right here. Capital R means rotate. We're going to rotate around the origin, and we're going to go 90 degrees. A positive rotation is a counterclockwise rotation. We're going to turn it this direction around the origin, counterclockwise. I'm going to move one of the corners, and then I'll pause the video for you to move the other two corners of the triangle, and we'll see where it ends up. Okay, this dot right here, I'm going to move 90 degrees counterclockwise. To do that, I'm going to connect to the origin and then make a 90-degree angle coming up like this. It ends up right there. That is a 90-degree angle that I formed with these blue lines that you see. I'm going to pause the video, and I want you to move the other two dots of the triangle to where they are over here in this quadrant of the grid. Connect to the origin, and then bend a corner 90 degrees and come out this direction. And here's the answer in blue ink. I'll pause the video for you to check your picture and correct it if you need to. Let's try one more of these. First thing you need to do is draw a triangle ABC onto the grid. Next, perform the dilation around the origin with scale factor 1/2. To do a dilation, when you have a coordinate grid, you use the coordinates. Multiply the scale factor by those coordinates. So let's say I wanted to find the image of point A. I take the ordered pair for point A, which is 2, 1, and multiply by that scale factor of a half. 2 times a half is 1, and 1 times a half is a half. So the image of point A with that dilation is at 1, a half. Over 1 and then up just a half. There's the green dot for that. I'll pause the video for you to do the same thing with points B and point C. Okay, please check to see that your drawing looks like the green triangle, and fix it if you need to. Next, we're going to do a translation. We're going to adjust the x-coordinate by 2 and adjust the y-coordinate by -2. Another way to think of that is to move right 2 and down 2. It's the green triangle that we're moving. So I'll pause the video, move that triangle right 2 and down 2. Okay, here's the result of that in blue ink. The last thing we're going to do is another dilation around the origin with scale factor 4. So take the corners of the blue triangle, multiply by the scale factor of 4 to see where this larger triangle ends up. Please show your work over here on the left side. So the final image is shown on the screen in black ink. That's the triangle you were trying to create. I'm going to pause the video here for you to check, first of all, your work to make sure you got the correct ordered pairs, and then also to check your final triangle to make sure it's accurate. Please fix anything that you might have missed. On the next page of the book is a vocabulary word that's a key idea for this lesson. A similarity transformation is a transformation which results in the pre-image and image having the same shape. All three of those problems that we did with triangle ABC were similarity transformations. Our final answer had the same shape as the original triangle. We've talked about two different kinds of transformations this year. In an earlier activity, we discussed congruence transformations. We called those rigid motions. Then in this section, we're discussing similarity transformations, a transformation that keeps something the same shape, but it could change its size. So in this Venn diagram, fill in where these four words go on those blanks. Notice that there are three congruence transformations. A dilation is not a congruence transformation. It's not in that circle of the Venn diagram. However, there are four similarity transformations. All four of these things are in the circle for similarity. Translations, rotations, and reflections are both congruence and similarity transformations. Two figures are similar if and only if one figure can be transformed from the other figure using one or more similarity transformations. The word similar in geometry means that two figures are the same shape, but they don't have to be the same size. Here are two rectangles. Are they similar? To decide if they're similar, we have to come up with a sequence of transformations that would map this first one onto the second one. They're not the same size, so one of those transformations has to be a dilation. What would the scale factor of that dilation be? Well, the length of this side is 4 units. The length of this is 6 units. 4 times 1.5 is 6. So our dilation would need to have a scale factor of 1.5. So K is 1.5. Let's apply that scale factor to rectangle ABCD to see what's created. Take the coordinates of each vertex and multiply them by 1.5 to see what kind of dots you get. Here in red ink is the rectangle after the dilation is performed. Over here on the left side, you see the work that I did. I took the ordered pairs for A, B, C, and D and multiplied the x and y coordinates by 1.5. Then I graphed the results. That created this red triangle. Now that we have the correct size, can you think of a transformation that would move this red triangle onto this final triangle? That transformation could be a reflection where we flip it onto there, or it could be a slide where we're simply sliding it to the right. Either one would work. There is a vertical line of reflection that runs right in between the shapes. So if we want to use a reflection to flip that red one onto the black one, then we would be reflecting over the line x equals 5. So because it is possible to make the one rectangle land exactly on the other, then we would answer this question yes. They are similar, and our reasoning is because of these specific transformations that we did. So in this lesson, we discussed similarity transformations. It's a way to decide if two figures are similar. If you can find transformations that map one figure on top of the other, then we say yes, the figures are similar.